two topics to understand. The topic of mixtures. So as you know, all matter is composed of different kinds of substances, and everything in the universe is made up of matter. Now, the only thing that doesn't have matter is vacuum. Other than that, everything is composed of matter. And matter can be classified into two big groups of substances. And that is either pure substances or mixtures. Now, in this chapter, you should have learned that pure substances include all of the elements in what we're going to call the periodic table of the elements, and we're going to take a look at that today. And mixtures are simply combinations of substances, whether they are pure or not pure, into things that you can call homogeneous mixtures. A mixture that shows no difference in the components, or a heterogeneous mixture, which is a mixture in which you actually see the components coming. And if you did your homework and the quiz for this chapter, you probably saw questions related to this idea of mixtures. So again, this is going to be a quick review of chapter 3 because we really are here today to talk about chapter 4. So all of matter can be classified into either pure substances or mixtures. And then pure substances, there's two kinds. One that we're going to call elements, and that's what we're going to talk about in chapter 4, or compounds. And then mixtures can be either homogeneous or heterogeneous. And I'll give you one example of each, just to sort of get your bearings. So elements are things like hydrogen, gold, lead. Those are, probably you cannot see down there because of the screen, but those are pure substances of the kind known as elements. And we're going to find these guys in the periodic table. Now, compounds are combinations of elements. These are two or more elements combined. So for instance, water is a compound. It's a pure substance because it's composed of only a fixed number of chemicals that we know its composition. We actually know that eventually in this course are going to learn that that is described as H2O, and we're going to learn what that means as we progress in this course. Mixtures are not pure substances. They are a couple of substances that are pure but that are combined in different ways. So for instance, a homogeneous mixture would be something like water plus salt. If you think at home of getting some water in a glass, and then you add some salt to that water, and you mix it, you stir it, that salt disappears. We call it dissolves. And when you don't see the salt, and you only see what appears to be the water, you have a homogeneous mixture. How do you know the salt is there if you didn't do the mixture? Well, you take a little bit of a taste and it's gonna taste salty. So it's a mixture in which you cannot see the components. A heterogeneous mixture is a mixture in which you can actually see the components. So for instance, I often give this as an example because it actually gives you the idea that sometimes this term can be subjective. In other words, it means something to some of you, but it may mean something else to somebody else. So for instance, spaghetti sauce. I would have to probably emphasize that that spaghetti sauce is chunky. It has chunks of tomato and onion, and you can see it. Because if you put that in a blender, and then you turn on the blender to high power, and then you look at the mixture, you may say, oh, this looks like a homogeneous mixture. I cannot see the components. So that's a little subjective. And that's where you have to be careful with that. Now, with this quick review in mind, let's take a look at that first question. From the homework.
Professor Marty, what's the difference before homogeneous and heterogeneous? What's the difference?
The difference is in the homogeneous mixture, you cannot tell if there's two or more things present. You cannot see the components. They're all mixed in evenly. So like the salt and water. And in the heterogeneous, you actually can see the components. So if I take, for instance, some sand from the beach, and I look at it carefully, I can see that there's different kinds of grains. Some of them are lighter, some of them are darker. That's a heterogeneous mixture because I can see that there are more than two components there. Can you guys think of another example of a heterogeneous mixture?
Hetero is that you can't?
That you cannot, that you can see the difference in the components. Homo is that you cannot see the difference. Very good question.
What was for heterogeneous?
You can see all the different.
Right. Heterogeneous, you cannot, I mean, you can see the difference. Right. Well, let me give you examples of mixtures, and then you tell me if you think they're homogeneous, you cannot see the components, or heterogeneous. For instance, this screen is a mixture of compounds, of chemicals, of substances. Is it homogeneous or heterogeneous?
Homogeneous.
So you cannot see that there are two different materials here. If you look at it, at the screen, I mean, it's subjective. So Cici, you may be right. You may actually say, no, I only see one even thing. But somebody may say, well, but wait a minute, I see white stuff here and dark stuff here. So it's still part of the screen. So the screen is a heterogeneous mixture because I can see that there's two components. It's still one material. And then the back is kind of shiny, the front is not shiny. So two or more components that you can actually tell them apart.
No, it is a heterogeneous.
So it is, but you could actually argue, well, I think it's homogeneous because I'm only looking at the white part, not at the black part. Let's take another example.
The light.
So the light,
Yes.
okay. The light is a little tricky because the light is composed of very tiny particles known as photons. I would argue that light is homogeneous just because you cannot see the different components. You just see either white light or red light or blue light, but you don't see the parts. You see them all as one substance. It is a substance, and it's a very tricky one. So we'll hopefully find that question soon and see what program says. But What about the paint that is on this wall? Is that a homogeneous mixture or a heterogeneous mixture? Look at the paint. And it's your opinion. There's no right or wrong here.
Homogeneous, we just see one color.
You just see one color.
Yes.
If you cannot see the different components, then it's homogeneous.
What about when you make a cake?
Well, I mean, it depends on the cake. But most cakes, you can actually see
Yes.
that there's different textures, different components.
Oh, okay, when you see the different tests, the different components.
Then it's heterogeneous.
Heterogeneous.
If you see a cake and it has frosting, then you can see two different things. The whole thing is called a cake, but the frosting and the actual inside of the cake are two different things that you can tell apart. So it's heterogeneous. Well, what about mayonnaise? Or even ketchup?
Homogeneous.
They look pretty much like one thing only, right?
Yeah.
You cannot see the egg and the oil and the mustard. So mayonnaise has many different ingredients, but you don't see the different ingredients.
What about ice? Ice is a.
Well, you look at ice, and ice is actually not even a mixture. It's a pure substance because it's made up of only water, only one chemical. So if there's no more than one chemical, then it's a pure substance. And then you have to determine, well, is it an element or is it a compound? 155 degrees Fahrenheit to degrees Celsius. And that's the formula you need. Equals 155 minus 32 times 5 divided by 9. Now, it is important that you do this in the order that you see it here. So we're gonna do first the subtraction. So please have your calculator ready so that you know how to use your calculator. We have 155, and I'm gonna subtract 32 from that, and that's 123. And that 123 is gonna multiply it by 5, and then it's gonna be divided by 9, and that's gonna give us the answer. Now, from this point on, it doesn't matter if you first divide and then multiply, or first multiply and then divide. Multiplication and division order doesn't matter, as you know. So 5 times divided by 9. And I get 68.33. Now, at this point, the problem was asking us to report the answer to 3 significant digits. So, we're gonna report these to 3 significant digits. What would that be?
68.
That's how many significant digits? 0.3. That's 3. So 68 only is 2 significant digits. We need one more. 0.3. So matter can exist in 3 physical states. It can exist as a gas, as a liquid, or as a solid. And I want you to think about this for a minute, because we're gonna find that the process of going from one state of matter to the next actually has names. I'm gonna put a container, an imaginary container. And I'm just gonna use a generic substance. You know, you could think of this as water. All of these 3 squares represent the same substance on their different states of matter. On the gas state, the substance composed of these dots has all of the components spread out through the entire container. In the liquid one, the components are still spread out, but they're confined to a space much smaller than the container space. Okay? In other words, the molecules, the components, the pieces, the fragments, are closer together. In the gas, they're far apart. In the liquid, they're closer together. And in the solid, not only they are very close to each other, but they are arranged in a particular geometrical arrangement. Okay? So, if we think of this as water, this is going to be the steam, this is going to be the liquid water, excuse me, and this is going to be this water turning to ice, one ice cube. Now, the process of going from gas to liquid is called condensation. The process of going from liquid back to gas is called evaporation. The process of going from liquid to solid is called solidification, or there's another name. Let me see if it comes to me. I'll look it up in a second. And the process of going from solid to liquid is called melting. I remember. It's also called freezing. But it's freezing where we typically apply it to water. Although it can be applied to any liquid that becomes a solid. Now, before we wrap this up, this is a mini lecture on states of matter. I want you to think of heat energy. So, when we turn on the heat in fall and in winter, we start warming up a room by introducing heat. Heat is energy. So I want you to think for a second here whether or not you need to remove heat or add heat to go from one state of matter to the next. So, do we need to add heat or remove heat to go from gas to liquid?
Remove heat.
So in other words, we need to cool it down,
Yes.
right? Correct. To go from liquid to gas, we need to warm it up. So in chapter 3, we talked about matter being everything that is in the universe, and that one type of matter can be classified as pure substances, and that one kind of pure substances is something that we call elements. So what are elements more specifically? Anything that you see here is an element. All of the matter in the universe is composed of combinations of those elements. So when you think about your own body has water, your body has proteins, your body has fat, whether or not we want to admit it, we do and we need it. It has all kinds of other chemicals, but all of them are composed of these basic elements. Some of them are more common than others. Okay? Now, different elements have different names, and they also have different symbols. The good news is that in modern chemistry, you don't need to memorize any of these. You have access to this table, you look it up, you use it as a tool. you use a table of the periodic elements the way you use a calculator, okay? So when you use a calculator, you're basically using a tool. The periodic table is also a tool that we're gonna use. So, let's talk about the names of the elements first, and then we talk about the symbols. So, on this big box, you see one example of an element called beryllium. Weird name. You know, we don't encounter this name in everyday life. I don't know any person called beryllium, personally. I mean, for that matter, I don't know anybody called lithium, although that would be kind of a cool way of naming your children, you know, naming them after elements in the periodic table. But they do have an origin. They come from somewhere. These names come from somewhere. Now, this is not a history lesson, so I'm not going to tell you where the names come from, but I'll give you a couple of examples. So, for instance, let me pick one that is somewhat sensible. One of the more modern ones. I don't see it. It's way down here, so let me scroll down a little bit. So this element is called Californium. Californium. That sounds like a state. California, Californium. Well, it turns out that Californium was discovered in California. So they named it after the state. So many of the other names also have either the history of who named them or some ancient Greek history. There is, let me see, most of the ones that I think make sense are the ones that are named after countries or people. Polonium is named after Poland. Where is curium? Curium. I don't even see it anymore. That's named after Marie Curie, who discovered curium. I can't believe that I cannot find it. Now, if you notice, all of the elements have a symbol. And some of the elements have a one-letter symbol, some of the elements have 2 letters. There's no elements with 3 letters unless they are temporary elements. So, either 1 or 2 letters. They are listed in this table in an order of size. This is important because different elements have different sizes in 3 dimensions. The smallest of all the elements is called hydrogen. And it's at the top left of the table. It doesn't matter where the table comes from. If you go to Japan and you look at the periodic table, it's going to have hydrogen on the top left. It doesn't matter where you are. And it's the smallest element. They start getting bigger as you go to the right and to the bottom. So the next element in size larger than hydrogen, but the second smallest, if you will, would be helium. Now notice that there's a number on top of the symbol. So on top of the H, there's a 1, right? Okay. Everybody sees that. On top of the HE for helium is a 2. Now where is number 3?
It's
The first column.
In the first column,
Yeah,
the second element.
Yeah.
Very good. Now, you just discovered something, Cici, that is going to help all of us. You refer to this as a column to give me a location, right? You said first column. That's excellent. But that first column is going to be called a group. We can call it a column, that's fine. But they're called groups
In chemistry?
in chemistry. So this is group 1, group 2, and it has numbers. You can see them there. group 3, group 15, group 18. So the next time that I ask you for the location of an element, you're gonna tell me is in group and then the number, and then here comes the second one. I didn't hear the word row, but this is the first row, the second one. We're gonna call those period. Yes.
Do the homework grades, do those go to our like real grade? Our final grade?
The homework grade does count for your final grade, but you can do the homework as many times as you want to until you get 100. You just have to complete every attempt before you can have a second or a third attempt. Does that make sense? If you don't complete it, then you cannot open a second attempt. You have to complete it and submit it. With the quiz, you have 2 attempts only, okay? Once you open the first attempt and finish it, you have a second attempt. Once you complete the second one, that's it. Whatever grade you get, that's the grade you get. Okay, so we're gonna call these columns groups, and these rows, we're gonna call them period, or periods. Oops. Okay? Okay, so where is the element with the number 4 on top of the symbol? Where is it located? Tell me the group and the period number.
Which one you asked, which element?
The one with a number 4 on top.
It is in the group 1.
In group 1, okay? Where is it?
No,
I
no,
don't
it's
see
not
it.
in the group 1. You say the 4, no?
With the 4 on top.
4 on top. Okay, he's in the second group.
Second group, group
Yeah.
2, okay? And
Yes.
what period?
I think.
These are the period numbers. 1, 2,
Oh, period
3,
2.
4. So period 2, group 2, yes, that's where it is. Those are the GPS coordinates of this guy. Now, tell me what element is found in group 13, period 3. Group 13, period 3.
Aluminum.
Somebody said aluminum. I think it is. I looked briefly. So I said group 13, period, oops, 3. Group 13, period 3, it is aluminum. Now, what is the symbol of aluminum?
AL.
Right there. Al. Aluminum, Al.
You have to say lowercase al because it can be.
That's another important distinction. When the symbol has only one letter, it's a no-brainer. It's uppercase. So if it has only one letter, carbon, hydrogen, nitrogen, oxygen have only one letter, it's always capitalized, always uppercase. If it has 2 letters, the first letter is uppercase, the second letter is lowercase, always. So yes, capital A, lowercase l. Now, what is the number on the top of the symbol for aluminum? What number do you see on top of the symbol?
13.
13. Now I'm going to put it right here. Now it's going to get a little bit more complicated now because there's another number associated with every symbol. And that's a number that is not a whole number. It's actually a number with decimals. What number do you see on the bottom of the name aluminum here?
26.
You have really good vision if you tell me that. Because I had to get
982. And I have some type of vision problem.
That's pretty good. 26.982. This number is also gonna become important in this chapter, and we're gonna talk about it in a few minutes. So, that's it. Whenever you look at a symbol, you're gonna describe the element with 4 different identifiers. The name, the symbol, the top number, which is gonna be called the atomic number. So this top number has a name. It's called the atomic number. And it's unique. It's the social security of the symbol. It doesn't change unless you change symbols. And then the bottom number, which has more than one name, unfortunately. I'm gonna prefer one, but I'm gonna use more than one. It's also called the atomic mass, but sometimes it's called the molar mass. And unfortunately, sometimes it's called the mass number. So it has like 3 different names. I'm gonna prefer the one of these 2, atomic mass or molar mass. So before I move on, can you find the element, just to have another one here for comparison? In group let's say 15, period 2. What element do you see in group 15, period 2? You can give me the name or the symbol. So group 15,
Nitrogen?
period 2.
No, no nitrogen. What is? No, that.
That's period 2.
Yes, nitrogen.
Period 2. Be careful because you have to follow from the left. So it is nitrogen. You had it right the first time. What's the symbol for nitrogen?
It's on the top. It's 7.
No, the symbol.
The symbol N. Roman sign.
I'm gonna put the name on the bottom. Actually, this table, I'm sorry for distracting you, but this table uses the British spelling, aluminium. It has an extra I that I didn't put here. I called it aluminum instead of aluminium. Same thing, just 2 different spellings. Okay, so nitrogen. Now, so that's the symbol. What is the atomic number?
7.
The atomic number is the number on the top.
7.
It is in fact 7. And what is the molar mass or the atomic mass?
007.
That's right. Good eyesight. Well, yeah, it's really small. 14.007. Excellent. That's the atomic mass or the molar mass of nitrogen. So with those 2 as an example, let's take a look at why they are smaller elements, and then larger elements, and then bigger and bigger and bigger. So you get larger from left to right and from top to bottom. The atomic number gives you a hint that is a bigger atom. So the larger the number, the larger the atom. But what makes them bigger or smaller? What's the real reason behind that? Well, let's talk about that. And for that, I'm gonna turn this off for a second. And you guys, you need to do your part. You need to read the book, go over the lecture notes. Whether this is a face-to-face course or online, I know it's face-to-face, you still have to do the reading. That's always been true of any courses. So, I'm gonna do a cartoon depiction of the simplest atom of all. And I'm gonna describe hydrogen using a cartoon and then a list of properties. Actually, a list of properties first and then the cartoon. So here are the ingredients of hydrogen. Every hydrogen atom has at minimum 2 ingredients, but sometimes 3 ingredients. So every atom, not only hydrogen, but every atom has protons as one of the ingredients. I'll tell you in a minute what is a proton. It has electrons and sometimes, actually all the time except for hydrogen. Hydrogen is kind of weird. Sometimes in the case of hydrogen, but always in the case of other elements, neutrons. Now, if you're kind of nerdy and you look at science as a hobby, you may have heard of other ingredients like positrons or muons or ups or downs. There's all kinds of really strange things.
There's a neuron.
Yes, but this is the 3 that we need to know about in this course. Now, what are protons, what are electrons, and what are neutrons? Well, I call them the ingredients, but they're called, so this is going to be called an atom. All elements are composed of atoms. So hydrogen is composed of hydrogen atoms. What is an atom? It's the smallest piece of matter that you can divide a substance, a sample, using chemical means. There's other means. We're gonna call them physical, but chemical means allow you to divide matter into smaller and smaller and smaller pieces until you get to the smallest piece called the atom. But it turns out that the atom can be smashed even to smaller pieces, not by chemists, but by physicists. And when you smash an atom, you get these 3 things called the subatomic particles. And there's 3 of them that you need to know about. Now we're going to describe these subatomic particles in terms of 2 properties in a few minutes. But first let me give you the cartoon. So, and this is just a cartoon. This is an imaginary way in which an atom looks like. We never seen it. This is just a picture to help us visualize what an atom may look like. At the center of the atom, there's an area, and I'm going to draw a circle to show it, called the nucleus of the atom. It really doesn't have a boundary. It doesn't have a boundary like I put here in this cartoon. It does not have a boundary. It's just a region. In that region, you're going to find a particle known as the proton, and sometimes a particle known as a neutron. So I'm going to put a neutron here, but keep in mind that not all atoms of hydrogen have neutrons. So this is a neutron. Now, outside of this center known as the nucleus, there's a cloud. It's a big cloud. Actually, also has no limits. That cloud can be as big as the universe. But for purposes of understanding, we draw it as a cloud with a contour, with a border, if you will. Somewhere in here, and it can be anywhere in here, you're gonna have a smaller particle. I'm gonna draw it as a dot instead of as a circle. And that's gonna be called the electron. And this whole area is gonna be called the cloud or the orbit, or orbital. So what's the take-home message here? That every atom, starting with hydrogen, has protons, electrons, neutrons, that those are ingredients of the atom, and that those ingredients can be found in two different locations, either in the nucleus, which is in the core, or in a cloud or orbital, which is a bigger area surrounding the atom. In that bigger area, you can have the electron. In the core, you can have proton and neutrons. Okay. Now we need to talk about those particles, the subatomic particles, and describe them with two particular properties. And this is something that you have to, when you finish chemistry, you better remember this. It's not that I'm asking you to memorize it. I think it's something so fundamental that if you finish this course and you don't remember this, then I didn't do my job and you didn't do your job. You have to remember this. So, the three subatomic particles have two different properties that we need to remember. One property is going to be called the electrical charge. I mean, everybody has seen a battery, right? And you put it inside of a device to provide it with energy. That battery has potential energy, but once you put it and turn on something, it becomes kinetic energy. Now, you know that those batteries have a positive end and a negative end. Well, electricity comes in positive and negative charges. So I don't need to explain to you what that means. Just think of it as positive being the opposite of negative. And we're gonna give it a value of 1 for every particle. So protons have a charge of 1 plus. Every proton has a charge of 1 plus. It's a positively charged entity. Okay? Every electron has a charge of also 1, but is negatively charged. So electrons are negatively charged with a charge of 1. Each electron, 1, 1, 1. And neutrons actually are neutral. They don't have a charge. So they have a charge of 0. They're not positive, they're not negative, they're neutral. That's one way of describing these three ingredients. But there's a second way, and that is by describing the mass. How heavy are they? Well, you know that in the first part of this course we talked about grams. I'm going to show you the mass of a proton in grams. And then I'm going to make your life much easier. Actually, I don't need to turn it on. I'm just going to copy the number. The mass of a proton, according to the internet site that I just went to is 1.67 times 10 to the negative 24 grams. That's an incredibly small number. 0.000000024 times, then 1, and then 6, and then 7. Well, imagine I didn't wait long enough. Now he got angry. Letting me turn it off. Imagine if I were to actually put this number here and then ask you, hey, you need to memorize that. No. We're gonna use something called an atomic mass unit. And never mind what that is called, but I'm gonna put it here, AMU. Those are the units of this number that I'm gonna put here. And 1 AMU equals this number. So, the proton has a mass of 1 AMU, which is this whole number. It really doesn't matter. We're not gonna bother with that. We're just gonna say that the proton has a mass of 1. And the electron in AMUs, don't write this down because I'm gonna erase it, has a mass of 0.0001. Don't write it down yet. And the neutron has a mass of 1. Same mass as the proton. In other words, a neutron weighs as much as a proton. 1 and 1. But this guy is interesting because he's 1/10,000 of a 1. Because this is an introduction to chemistry and we're not gonna need that level of precision, I'm gonna tell you something that you know is not true, but is practical. This number is very small compared to that number, right? We would need 10,000 of these to match one of these. So we're gonna make our lives easier, and in this course, we're gonna say that the mass of the electron is 0. That's a lie, but it's a convenient lie. We're just gonna leave it at that. The mass of the electron is negligible, it's very tiny, so it doesn't matter if we call it 0. Understood? Okay. Now, you need to put your thinking caps on because I'm gonna ask you a thinking question. Look at this cartoon. This is hydrogen, and I'm gonna erase the neutron for now because this type of hydrogen that I'm drawing here doesn't have a neutron. It's the only atom in the universe that doesn't have neutrons, and is the most common hydrogen atom out there. So I want you to tell me, based on this cartoon, so there is a name of the compound, of the element, the symbol. I want you to tell me the mass of this and the charge, the electrical charge of this cartoon. So look at the cartoon, look at this table, and answer this question.
The electrical charge is a negative.
The charge is what?
Negative, because
Okay, so Cici says that the charge of hydrogen is negative.
because we have a positive one and a positive one and negative one.
So then the charge is negative. If you have +1 and -1, add them up.
No, it's zero. Yeah, it's
You
zero.
got it. You're thinking, which is great. You said, okay, it's negative because we have a -1 and a +1. Oh, wait a minute, then it's not negative, it's 0.
Yeah, it's zero.
So let's fix it. The charge of hydrogen, as per this cartoon, is 0. And that's fact. That's in fact true. What is the mass of hydrogen according to this cartoon?
1.
Yes. So the mass of this hydrogen as drawn on the board is 1, because there's only one proton. And the electron doesn't have any mass. So one of these, this one doesn't add up anything, this one there's none. So it's 1. Okay. Now, we're gonna move on to a different element. And we're gonna do the same thing. But then we're gonna come back to hydrogen, and with that we're gonna probably finish the lecture. So bear with me another 30 minutes or so. If you need to go and drink water, feel free to do so. I'm on a roll, so I'm just gonna keep going. I don't wanna lose my... Okay, so now we're gonna change this. And we're gonna add another proton. Now we have 2 protons. Okay? We're gonna add another electron. And I'm gonna add 2 neutrons. This is no longer hydrogen. This is no longer hydrogen. It's a different chemical. And we're gonna learn together what that chemical is. Now, for hydrogen, I'm gonna put the symbol of hydrogen here. The one on top, which we said was called the atomic number. And then there was a number on the bottom, 1.0, let me look it up in the periodic table, 1.008. And we said that this was the atomic number. This is super crucial today. I cannot emphasize this important next topic enough. It's super important. The atomic number of an element is always equal to the number of protons in that element. So, hydrogen has an atomic number of 1 because it has 1 proton. In other words, if an atom has 1 proton, it has to be hydrogen. It cannot be anything else. Is that understood? The number of protons gives you the identity of the identity of the atom. The number of protons equals the ID. And the atomic number gives you the number of protons. So if I put back the periodic table, let's put here a symbol for this element, and we don't know what it is yet. We're just gonna call it X. You're gonna tell me the mass and the charge, but also the number. Also the number. Look at this cartoon. How many protons do you see on my new cartoon? 2 of them. So would that be the mass, the charge, or the number? I just told you what the atomic number was. The atomic number is the number of protons. You just told me that this has 2 protons. So what is the atomic number of this element? If it has 2 protons. Come on, be confident. I see 2 people signaling, like, catchers in baseball.
2.
2. So the atomic number of this cartoon tells me that I have 2 protons and the atomic number is 2. Well, what about the mass? The mass is defined as the number of protons and the number of neutrons, but not electrons, because electrons have a mass of 0. So I have 2 protons and 2 neutrons, each weighing 1. So
4.
2 plus 2, 4 is the mass of this element. What about the charge of this element? It has
It's
2 protons, 2 neutrons, and I put 2 electrons actually. 0 plus 2 positives plus 2 negatives. When you add them up, they cancel each other, so the charge is 0. Now, what is X? Well, that imaginary element has 2 protons, so it has an atomic number of 2, so it has to be the element with the 2 on top. Where is that element? It's right there, right? He, helium. Helium is the cartoon that I have now here. So X is actually helium. And I'm going to write the symbol as He for helium. Now, if I use the symbol as per the periodic table, it's written like this. He, it has a 2 on the top, and then it has the name helium. And then under helium it says 4.0026. How come it doesn't say 4? Why does it say 4.0026 instead of 4?
Is it scientific number? You should have put it on the bottom.
Well, it's more than that, but that's a good start. See, when we wrote the symbol for hydrogen, hydrogen has a 1.008, not a 1, as the atomic mass. So why? We're gonna go back to hydrogen to explain that, and that's gonna bring us to the conclusion of this chapter. So, I'm gonna erase that. This is not a trick question, it's a question that is gonna test whether or not I'm making any sense. I'm gonna erase that. And this is my new drawing. This is my new drawing. And I want you to tell me the mass of this new drawing, the charge of that new drawing, and the atomic number of that new drawing. So, let's start with the atomic number. The atomic number is the number of protons, right? So what is the atomic number of that new cartoon? I only have 1 proton, 1 neutron, 1 electron. What's the atomic number?
1.
It's not a trick question, it's a 1, right? What is the charge? You have 1 proton, 1 plus,
0.
1 electron, 1 minus, neutrons have no charge, so the charge is 0. But now, when we had another cartoon, the very first one of hydrogen, it had a mass of 1, right? But now I added a neutron. The identity has not changed. It still has atomic number 1, so it's still hydrogen. Remember, the hydrogen, the number of protons is the ID. But now the mass number is what? 2. Not 1 anymore. It's still hydrogen, it's just a heavy hydrogen.
Can I guess what the element is?
Yes, what is the element?
H2O. It's not H2O.
H2O, no, that would be a molecule.
No, wait, because it's number. Oh, I totally forgot though.
The atomic number tells you the identity. The atomic number is 1. What element is that?
It,
It's not a trick question.
we did in the first city. Alien as.
It's not helium. So look at the periodic table.
Yeah, I was gonna say.
It's a periodic table, no, it's not. What was the element that we put at first, the first
Hydrogen.
cartoon? Hydrogen. So it's hydrogen, it's still hydrogen. So this guy is still hydrogen. Because he has one proton. If he has one proton, he cannot be anything else. He cannot be water, he cannot be helium, he cannot be gold. One proton means hydrogen. He can have 50 neutrons if you want. Super heavy hydrogen, but it's still hydrogen. It doesn't matter. The protons tell you the identity. Oops, what was that? The number of protons tells you the identity of the atom. Don't forget that, please, today. Now, it turns out that the mass of this heavy hydrogen is 2. Well, I'm sorry for making this a little bit more complicated, but I'm gonna add one more, and I'm not gonna draw the cartoon. I'm just gonna tell you the properties of 3 different atoms, and then you're gonna tell me what they are. We don't need this anymore. So I'm gonna put X1, X2, and X3. And right below that, you're gonna put the symbol of the element with the following information that I'm gonna give you. Number of protons, number of neutrons, and number of electrons. I'm going to give you all the information for you to tell me the symbol of these atoms. So this first one, X1, has 0, 1, and 1. X2 has 1, 1, and 1. And X3 has 1, 2, and 1. So let's take a look at the first one. What's the chemical symbol of the first element if it has 1 proton? Not a trick question. It's a yes.
What?
Yes, but what is the symbol? What is the element? H. So we said hydrogen has 1 proton, so it has to be hydrogen, right? All right. What is X2? Another trick question. It's H. It looks like a trick question, doesn't it? It looks like I'm trying to trick you, but I'm not. I'm trying to make a point. And what is number 3?
H.
X3 is also H. All 3 of these atoms belong to the element hydrogen. They're all hydrogens. They're sort of like twins, if you will, or what's the name for when you have 3? Triplets, yes. But one is a little bit heavier than the first one, and then this is the heaviest. Why? So if we put the mass of these guys, what's the mass of the first one? 1. What's the mass of the second one? 2. What's the mass of the third one? 3. So this is a heavy hydrogen. This is an in the middle hydrogen. This is a light fit, if you will, hydrogen. Okay? All of them are real. All of them are part of the universe. The reality is that 99.9% or more is like this. some other percentage is like this, and some other percentage is like this, but very small percentages. Why all of this complication? Well, because if you remember, the symbol for hydrogen has a 1 on the top, meaning the atomic number is 1, but in the bottom, it has this number. It doesn't have a 1, it doesn't have a 2, it doesn't have a 3. It has a 1.008. So do you guys know what is an average?
Yes.
What is an average?
It's not, average is not high and low, it's between. That you said, okay, when we get all those combined, the protons, neutron, we have to put an average.
Okay, so let's do this. I'm gonna reveal something personal about myself. I'm 59 years old. I'm an old guy.
No, really.
You wanna share your, Sean, your age? Age?
19.
Holy moly. So, I was 40 when you were born, right? Yeah. Okay, fine, thank you for sharing that. You wanna share your?
43.
Okay. How about you guys? You wanna share?
18.
8. We have. Is that the baby of the group? How old are you?
18.
Okay, we have 2. Now, what's the average age of this group of 5 people?
18.
That's not the
Let
average.
me check.
Oh, 43.
That is called the mode.
Okay,
The
43.
mode is the most common number, but not the average. So the average is that plus that plus that plus that plus that divided by 5.
31.4.
I contributed a lot to this age average, so that's why it's biased. The 18 and the 18 are called the mode. It doesn't matter. This is not a math or statistics class. But it's important that you know what is an average. An average is the sum of numbers divided by the total number of numbers. So that plus that plus that plus that plus that divided by 5 gives you the average. Okay. So keep your thinking caps on. If I give you these numbers, 1, 2, and 3, and I ask you for the average of those 3 numbers, what's the average?
We add them and then we divide by 3.
You add them and then you divide by 3. 1 plus 2 is 3, plus 3 is 6. 6 divided by 3, the average is 2, right?
Yeah.
So this number should be 2, but it's not. Why? This is actually the average, but it's not 2. What is wrong with this? There's nothing wrong. This is a simple average. This is a simple average. If I want a better average,
Times 1,000.
I need to do, well, you're close, but not quite. I need to do something called a weighted average. So for instance, in this average, I have 2 people of the same age. So these are contributing more to the average than the rest of us. So if I wanted to calculate a weighted average, a better average, I would have to take that in consideration. And I would do actually a percentage of people with a different age. So I don't want to go with this because that would be complicated. I'm just gonna simply explain to you what is a weighted average. That number is a weighted average of these 3 numbers. But it's not 2. Here comes why. So I'm gonna see if I can find the actual contribution of each hydrogen to the mass of hydrogen. And then we'll wrapping it up. It's just that it's gonna take longer because this is a complicated concept, if you will. Gotta pull that way. So in a weighted average, you have to do something. You have to do the following. You need to take the mass of each atom so the mass of each of the simplest hydrogen is 1. The mass of the next one is 2. The one with 1 proton and 1 neutron. And then the one with 2 neutrons and 1 proton is 3. But then we need to take into consideration something called the abundance. The abundance. And that is in this little corner of this graph. Let me see if I can make it a little bit bigger. So the most common hydrogen, the one with no neutrons, exists in nature at a rate of about 99.972%. So I'm gonna put that here. 99.972% of all hydrogen is of this kind, of the one with no neutrons. And only about 0.001 is of the second kind. And the third kind is almost nowhere to be found. So we're gonna put 0. It's not true, there's a little bit of it, but they call it a trace, meaning almost nothing, but it's out there. Now, new word for you guys today. These triplets of hydrogen, instead of being called triplets, they're called isotopes. So twins, triplets, quadruplets, in chemistry are always called isotopes. So these are different versions of the same atom, but that are heavier or lighter. And hydrogen happens to have at least 3, if not more.